Hi, I'm Dr. Edward Schwieterman at the University of California at Riverside. I'll be starting this workshop primer by speaking about stellar evolution through the lens of early Earth environments and prebiotic chemistry. This is important to discuss because the sun has changed with time, and thus the sun as seen by the early Earth was different than today. This has implications for the environmental conditions at the origin of life. I should note before I begin this talk that I'm not a stellar astrophysicist or heliophysicist. Rather, I'm an astrobiologist who studies planetary atmospheres and their evolution, habitability, and potential for remote biosignatures. Like the origin of life field, stellar evolution is a key factor in these topics. Particularly because this is the first talk in the series, I'm going to start this presentation with a tentative list of fundamental questions relevant both for this presentation and for the subsequent topics in this session. On this slide, I've listed some fundamental questions relevant to PCE3. The first is, what were the prevailing conditions in the early Earth environments relevant to life's origins? These could be physical parameters like temperature, chemical like pH or availability of precursor molecules, or it could be something like the surface fluences of UV photons that are important for prebiotic chemistry. The second, how did the environmental conditions shape the chemistry that occurs? This sort of understanding requires joining prebiotic chemists with planetary scientists. How common or rare are these environments elsewhere in the universe? This demands an understanding of the environments that exist elsewhere and requires an understanding of those planetary environments with their host stars. And can we extrapolate our knowledge of prebiotic chemistry as it may have occurred on Earth to other worlds in order to better inform the search for life elsewhere? This is one of the key goals of NASA's Astrobiology Roadmap and National Academy of Sciences Astrobiology Science Strategy. It's also another reason why it's important to consider both the evolution of our star and other stars as well. Why care about solar stellar evolution in the context of life's origins? The solar spectrum is a key input to all models understanding the conditions present on a planet. That includes the planetary climate, the surface temperature conditions, liquid water stability, or the needed greenhouse gas composition needed to maintain climates. The stability of that climate to escape given XUV radiation and energetic particles from the sun. The chemistry of that atmosphere, including potentially the delivery of metabolically important trace gases to the ocean through photolysis. And the surface UV environment, which may impact the generation and destruction of complex prebiotic molecules in early Earth environments. Before talking about the luminosity evolution of our sun specifically, I want to set our sun in context with other stars. So on the left is what's called a classic Hertzsprung-Russell diagram. It plots the luminosity of stars versus their surface temperatures. The line here is the main sequence. That's where all the hydrogen-burning stars lie. And the FGKM stars are indicated. Our sun is a yellow dwarf, or a G2V star, with a 5800 Kelvin photosphere. The population of stars in our solar neighborhood are actually tilted to cooler, redder stars, called M dwarfs. And in fact, G dwarfs only constitute about 12% of the stars in the galaxy. On the right is a graphic that depicts the relative abundance of stars in the solar neighborhood. The red stars are M dwarfs, the orange ones are K dwarfs, the yellow ones are G dwarfs, and then there are a few F dwarfs and A dwarfs. The luminosity of the star is highly dependent on the mass. It's dependent on mass to the 3.5 power. So effectively, when you look at the night sky, you're actually not seeing any M stars at all, and only a handful of sun-like stars. Mostly you're seeing the brightest stars that lie up to the left-hand side of the HR diagram. Those are actually the most astrobiologically interesting stars, in part because their lifetimes are so short. So the lifetime of the star is inversely proportional to the mass, to the 2.5 power. The fate of our sun is, unlike heavier stars which become supernova or black holes, is to become a planetary nebula and a white dwarf. And the amount of time that the sun will live is about 10 billion years. This is sort of the textbook definition of stellar evolution. You start off with a dense cloud of dust and gas that, due to a perturbation or another factor, that cloud of dust and gas begins to contract. Eventually, a protostar is formed and a disk. That time scale is 10 to 100,000 years. An active protostar and disk is called the T-Tauri star, and that can last from 100,000 to 3 million years. After that T-Tauri phase is over, there's a protoplanetary disk. This is the era of planet formation. On the right is a ALMA radio image of HL Tauri, which is a 1 solar mass star that's undergoing planet formation actually at 100,000 years. And so this is sort of rewriting some of the textbooks on planet formation, which you'll hear more about later in this session. Premain sequence stars are stars that are still contracting. They're not yet fusing hydrogen in their cores. On the left is a series of evolutionary tracks that show the evolution from the Premain sequence onto the main sequence. What you can see is that Premain sequence stars start off bright as they're radiating gravitational potential energy, and then get less bright as they enter the main sequence. You can also see that the amount of time it takes to go from the Premain sequence to the main sequence is highly dependent on the mass of the star to begin with. On the right is another way to visualize this. This shows the evolution of the Earth-Sun equivalent distance, NAU, for different stars from 0.08 solar masses, which is about the lowest mass a star can have and still fuse hydrogen in its core, to 1 solar mass, which is the sun's mass. As you can see, the stars start off with Earth-Sun equivalent distances that are far out. They come in as the stars cool down, and then once the stars enter the main sequence, they slowly brighten. However, for the lowest mass stars, their main sequence lifetimes are very prolonged and can last up to a gigayear. This is important when we consider the habitability and environmental conditions that may exist on habitable zone planets orbiting light-type stars. Once the sun stopped contracting, it entered the main sequence phase. Stars that enter the main sequence are held up by hydrostatic equilibrium. That simply means that at each layer of the star, the gravity pulling inward is equaled by the pressure of gas pushing outward. That gas pressure and temperature is supported by fusion reactions in the core that generate energy. The dominant fusion process in the sun today is the proton-proton chain. It's a nucleosynthetic process by which 4 hydrogen atoms, nuclei, combine to form 1 helium nucleus. In the process, energy and neutrinos are released. Over the course of the sun's main sequence lifetime, production of helium from hydrogen over time changes the core density and pressure, causing reactions in the core to proceed more rapidly, which expands the sun's radius and increases its luminosity. The standard solar model predicts that the luminosity of the sun has been increasing about 10% per gigayear. This is almost entirely the result of an increase in radius of the sun with time. So this is a plot on the left of solar radius versus the age of the sun from Bacall et al. 2001, which is one of the most well-cited studies on this topic. And on the right is a plot of the increase in luminosity of the sun versus time. And what this shows is that the luminosity increase is almost entirely a result of the increase in radius. The photospheric temperature of the sun has not changed drastically with time. What these plots, also from Bacall et al. 2001, show is that as the hydrogen fraction in the core is depleted, the temperature, pressure, and density in the core go up. This changes the rate of nuclear reactions and also their mode, The relative contributions of some branches of the proton-proton chain change, as well as the relative importance of a catalytic cycle called the CNO cycle, which on net fuses hydrogen into helium, but C, N, and O are important catalysts in this reaction. Ultimately, the prediction that the sun was 70% as bright in the Hadean has led to the faint young sun paradox. The faint young sun paradox is the apparent disagreement between the strength of what we would predict the CO2 and H2O greenhouse to be given a sun that's 70% as bright. So on the left is a plot from Follner et al. Follner 2012, Reviews in Geophysics, after an earlier plot by Sagan and Moeller in 1972. And this simply shows that if the CO2 H2O content of Earth's atmosphere were constant, if we simply decrease the luminosity of the sun, surface temperatures would fall below freezing about 2.5 billion years ago. On the other hand, Sagan and Moeller proposed that a highly reducing greenhouse gas-rich atmosphere would allow large surface temperatures even at these early times with low luminosity. That interpretation was found to be more in agreement with geochemical evidence, for example, oxygen isotopes from Church, that suggests that the Archean and perhaps Hadean oceans were incredibly warm, even substantially warmer than today, perhaps 50 degrees C or 60 degrees C or above. There have been many proposed solutions to the faint young sun paradox, some of which are viable and some of which aren't. One of the earliest attempts was by Sagan and Moeller in 1972, and they suggested that ammonia, maybe a highly reduced greenhouse gas, may be responsible for warming the early Earth. Ammonia is advantageous because it has a lot of absorption features in the mid-infrared window, which makes it an effective greenhouse gas. However, it's also easily photolyzed in the planetary atmosphere. So casting in 1982 and others since then have shown that the lifetime of ammonia in an early Earth-like atmosphere is probably too low to support the robust greenhouse needed to account for the faint young sun paradox. Another interesting solution is a massive early sun. The idea is that the sun started off perhaps several percent more massive and lost some of that mass over time. As we discussed before, the luminosity of the star is highly dependent on its mass, and so an early sun would be more luminous and potentially warm Earth to a greater degree. In addition, a more massive sun would mean that the Earth semi-major axis would actually be closer to the sun. Therefore, the flux experienced at the Earth is actually something like m to the 6.5 rather than m to the 3.5, if you do the math. This solution isn't widely embraced, in part because the rate of mass loss needed for the sun to have lost several percent of its mass is too great, considering observations of other early sun-like stars elsewhere in the solar neighborhood. There's almost universal agreement that at least part of the resolution to the faint young sun paradox is higher CO2 at early times. A crucial concept is the carbonate-silicate thermostat that has presumably regulated Earth's planetary climate over geologic time. The basic idea is that silicate minerals dissolved in rainwater, runoff on continents, react with carbonic acid derived from atmospheric CO2, producing carbonates which can be buried, subducted, and removed from the atmosphere. The volcanically active planet continually replenishes the CO2 via outgassing. The reason why it's a negative feedback is that as the temperature goes up, the hydrological cycle becomes more vigorous, weathering increases, and CO2 decreases, decreasing the temperature. As temperature decreases, weathering decreases, and CO2 increases, increasing the warming. The lack of continents as a source of silicate weathering at early times likely led to high steady-state CO2 on early Earth. The carbonate-silicate cycle system is also a crucial underlying concept for most conceptions of the habitable zone. It really seems like the most copacetic explanation for warm conditions on early Earth is high CO2, much higher than present. perhaps few percent to 10% or more in the early Archean, and maybe even higher in the Hadean. Many groups have examined the faint young sun paradox through exotic greenhouse gases, variations in planetary albedo, lack of cloud condensation nuclei. The climate modeling is really converging on the idea that once you consider 3D processes, some of the estimates for 1D models about the amount of CO2 you would need to warm the Earth are actually overestimates. So recent 3D modeling by Charnay et al. And others, Wolf et al. And others, has shown that once you increase the CO2 level, you actually have cloud feedbacks where you have fewer low clouds and more high level clouds. And this actually generates a stabilizing feedback wherein even though the luminosity of the sun is lower, the climate is stabilized at high CO2. Now, a lot of these modeling studies focus in particular in the Archean. In the Hadean, there are just not many constraints. And so the possibilities are more broad. There could be greenhouse N2H2 greenhouses, CO2 H2 greenhouses from volcanic outgassing of H2, impact generating, reducing atmospheres with substantial amounts of methane are possible as well. But what's clear is that the CO2 in the early Earth was substantially higher than modern day. When we think more broadly about what habitable planetary atmospheres look like on exoplanets, we may want to consider the fact that according to the traditional view of the habitable zone, the Earth is actually near the inner edge of the conservative habitable zone. And as you go outward, your flux goes down and you need more greenhouse warming in order to maintain climate temperatures. So we'd expect that if the carbonate-silicate cycle is the major geochemical feedback that maintains planetary habitability, that the CO2 will also increase as the flux falls off or as the distance increases from the host star. These curves show, the inner edge of the habitable zone is delineated by the runaway greenhouse, the outer edge delineated by the maximum CO2 greenhouse. And so one sort of assumption is that if we have habitable planets near the outer edge of the habitable zone, that they'll have high CO2 concentrations. This may be enhanced by the existence of other greenhouse gases, perhaps by impacts. But there's no geochemical feedback really that's been explicated that sort of matches the carbonate-silicate cycle, and seafloor weathering also, as in modulating greenhouse gas as a function of temperature. So this is a different view of sort of the same thing. This shows using a 1D radiative convective model, what is the minimum amount of CO2 that you would need in order to maintain surface temperatures of above freezing, so 273 Kelvin, as a function of the received flux of the planet and the photospheric temperature of the star, which controls the relative amount of blue light versus infrared light, and therefore changes the planetary albedo, which is why these curves change as a function of stellar photospheric temperature. And so Earth is at the inner edge of the habitable zone right now. And of course, we could have less CO2 and still be above freezing because our temperature is 288 Kelvin. So that's a lot warmer than the minimum that we're requiring. If we look at the Hadean Earth had 70% of the luminosity. And so this is predicting, CO2 concentrations between 1 and 10%, which is exactly what the climate models have converged upon. And then these crosshairs, this is interesting from the perspective of thinking about climates on other planets, the crosshairs are known exoplanets. So we would assume that if the carbonate-silicate cycle and greenhouse warming works the same way on other planets as it does on Earth and on Earth through its history, that most other exoplanets would have substantially more CO2 than exists on Earth today, or they'd be frozen. Okay, so we spent some time talking about the influence of stellar brightening on climate. And I want to spend some more time talking about how the UV evolution of the sun may have affected atmospheric chemistry and potentially surface chemistry. And one really important note here is that the UV spectrum, particularly at the shortest wavelengths, is not just a function of the temperature of the stellar photosphere, but it's also dependent on the activity level of that star. And so this is just a plot that shows the photon flux from a star of the same temperature as the sun, the contribution that comes from the black body, and then the contribution that comes from the chromosphere. And the chromosphere is the region of the star between the photosphere and the corona. And that's where the vast majority of this FUV flux is originating from. So the chromosphere dominates in this region of the spectrum. So these plots are from a review by Rebus and the IAU. And this plot over here shows the rotation rate of stars as a function of their age. So what we can do is we can look at different stars and what their spin rate is, and their rotation rate is directly correlated with their activity levels. So young stars rotate faster, leading to higher stellar activities. And you can see on the right plot, this is a measure of the flux density in ultraviolet regions of the spectrum, mostly for stars of various ages. So the sun is a relatively old star, and then we have several younger stars here. And what we can see is that in general, the younger stars are highly more UV active, FUV, XUV active than the sun. And so that has some extreme implications for atmospheric loss, atmospheric erosion, and atmospheric chemistry. And there are scaling relations that we can use actually to determine what the XUV flux and the Lyman alpha flux in particular of the star is as a function of its age. And this is coming from fitting observations of nearby stars, solar-like stars. So the XUV data taken of various solar analogs of different ages can be compiled together in order to model the expected evolution of UV fluxes on Earth as a function of the age of the sun. And so the top plot shows, as a function of different wavelength bands from the near ultraviolet to the X-ray, how much that flux would have changed as we go back in time. And what you can see is when we get to the Hadean, the XUV fluxes were substantially greater. Now, what's important to consider is that the shortest wavelength fluxes, those which are shown here, are most relevant for driving atmospheric escape and erosion. The longer wavelengths are the most relevant for atmospheric chemistry because they can penetrate lower into the atmosphere and photolyze important gases. This plot shows on the left an observation of E.K. Draconis, which is a young 50 million year old solar analog, and the modern sun in green, and in part based on observations of solar analogs like E.K. Draconis, a model of the sun at a young age is computed. And you can see that the fluxes at these UV wavelengths are substantially different between the modern sun and the 0.06 giga-year-old sun, particularly here at this Lyman alpha wavelength. The difference can be substantial. And this is important because on the right are the cross-sections, UV cross-sections for comparison, of several important gases in Earth's atmosphere today, many of which would have been there on early Earth. And so this UV radiation is incredibly important for driving the photolytic destruction and processing of these gases. To demonstrate that, on the right is a plot also from Clare et al. 2012 that shows a difference in photolysis rates between Archean and modern rates, just based on the different UV spectra, UV visible spectra of the stars. And so you can see that as we go to high altitudes in particular, where the highly energetic photons are being absorbed, the photolysis rates can differ up to 100% in terms of the photolysis of O2 and CO2, and substantial rates for H2O as well. In contrast, SO2 has a lower photolysis rate. So this sort of drives home the importance of including accurate UV spectra for photochemical modeling of early Earth atmospheres. These enhanced photolysis rates may have been really important for the delivery of species relevant to metabolism in the early Earth atmosphere. So the left is a plot of a photochemical model by Casting, presented in a 2014 paper that shows that the CO mixing ratio in the CO2 dominated atmosphere is over 10 ppm. And at that level, there's a significant amount of CO from CO2 photolysis being delivered to the ocean. And it's been pointed out by several authors that CO can be a really efficient metabolic source for primitive metabolisms. And indeed, acetogenesis using CO may have been one of the earliest metabolisms known to exist. So this is just an example that photochemical production of certain trace species in the atmosphere could be potentially relevant for early metabolism. If we expand our view a little bit, this may also hold true for planets orbiting other stars. M dwarfs have a different photospheric temperature. They're producing less NUV photons. But because of their high activity, particularly the young M dwarfs, they're producing a lot more Lyman alpha radiation, which would photolyze CO2 and produce CO. So CO2 photolysis might be more robust for active M stars with high Lyman alpha. And so CO and other prebiotic compounds like HCN and H2CO may be more readily synthesized on these worlds. And this has been explored by authors, including by Nava-Zdeno et al. 2016. In terms of the delivery of relevant metabolic species by interactions with energetic particles from CMEs, Erapetian et al. Modeled the impact of XUV and energetic particles on an early Earth atmosphere, that's primarily CO2 and nitrogen, and find that the production of NOx species is favored, including HCN, HNO, NO, and even some N2O. And so these may have been also important sources for fixed nitrogen in the earliest Earth environments. Finally, it's worth pointing out that the UV spectrum experienced during the early Earth is dependent in part on the state of the stellar spectrum, the intensity of the UV radiation, and also on the composition of the overlying atmosphere, which shields some wavelengths of light. So on the left is a plot from Maranjan and Sokolov 2016 that shows the solar flux at 3.9 gigayears. Almost all of the flux shortward of 200 nanometers is shielded out by CO2. And then the UV flux at the surface, with considering the atmosphere and then considering attenuation from water, 1 meter of water. And on the right is an absorption spectrum of pyrimidine ribonucleotides. And you can see that these are not constant in wavelength. Indeed, they vary in wavelength. And so the specific SED is perhaps an important thing to consider in prebiotic synthesis. And this is why we want to have our stellar models well calibrated for the epoch in which we're modeling. So the idea that the UV flux may have been an important consideration for the origin of precursor molecules on early Earth has been extended also to exoplanets, to planets orbiting other stars with different UV spectra. So this is a plot by Rimmer et al. 2019 in Science Advances. It shows in red the young sun spectrum. So you can see that again the radiation on that short word of 200 nanometers is negligible. Compare that with the dashed line, that's for the sun plus Earth today. The reason why the solid line and the dashed line are so different, of course, is because today we have an ozone layer. And so that blocks out much of this NUV radiation. However, for other stars with lower photospheric temperatures, they're producing a lot fewer UV photons. And so some reactions involved in the generation of precursor molecules, require a certain fluence of UV radiation in this wavelength range. And so given that, the authors have proposed that there is indeed an abiogenesis zone where that sort of formation of prebiotic molecules is favored because the temperature of the host star produces those photons. And of course, Earth lies within that zone, as we might expect, but several other exoplanets don't, because their host stars may lack that NUV radiation. Of course, there are some effects from flares which may push this abiogenesis zone down, so maybe an area worthy of further exploration. So to summarize, during the Hadean Aeon, we know from standard solar models and observations of younger sun-like stars that the sun was substantially dimmer, 70% that of today, and substantially more XUV active, with implications both for atmospheric escape and atmospheric chemistry. The dimmer sun has important implications for the composition of the early atmosphere, because we know that it must have had the greenhouse effect in order to create climate conditions. That means it almost certainly had much higher CO2 and potentially other reducing gases very early on in the Hadean. Lyman alpha and UV probably drove important photolytic processes that generated molecules important for early metabolism. The surface UV irradiances at wavelengths longer than 200 nanometers may have been crucial for the synthesis and stability of precursor molecules. And two things are important to consider there is, one is that the sun is actually putting out fewer photons at those wavelength ranges when it's younger, but we didn't have an ozone shield. And so, of course, the fluences at those wavelengths are higher. And other stellar types with different spectral energy distributions and evolutionary histories may be considered when extrapolating origin of life scenarios to exoplanet environments. And so the idea that the M-Dwarf's Premain sequence phase is 10 to 100 times longer is particularly important for things like atmospheric escape. And it may also be important for the generation of precursor compounds. All right. Well, thank you very much for your attention and joining us for this first primer talk. And so next we'll hear about accretion history and planetary dynamics by Rebecca Fisher, followed by a retinue of other talks, and a discussion meeting on Friday, October 9th at 1 p.m. Eastern Time. And then next week, there'll be another set of primer talks focused on the evolution of the near surface. And I've dropped the link to the workshop here. All right, thank you very much, and goodbye.